Namaskar.
Can you hear me as well?
What is the question?
Can you hear me?
Yes, I can hear you.
Yeah. Then there was an issue with the mic.
Hello, sir.
Hello.
Yes.
Good afternoon. Very
Yeah.
good.
Yeah. I think sir's voice is, not audible. Dr. Dinesh sir's voice.
Is it not audible?
Is it audible, Professor Dinesh sir's voice?
A little low.
Little low.
Yeah, but I can hear.
They have committed. They told me they'll be coming.
Okay. Yeah, we give a few more minutes to start with.
Hello. Acid office. Yeah. What is Ramesh's number? Ramesh Bhoja and Jagannathan. Cover 69. Okay. Fine. Let me.
I can see Sabachi, Sabiachi.
Subbasage.
Good afternoon, sir.
Good afternoon. How are you?
I'm good, sir.
Good.
Sir, Kara Abhishekaran will join.
Okay. Is Arvind joining?
Yes.
Okay. Okay, what we can do, I can start now and
Yes, sir. I think you can start, sir.
yeah.
I think we'll not wait. Okay, they had already told me they will join. Maybe they may join if we have to.
Okay.
If we wait, then it will be. Still, I'm calling them.
Sure, thanks for that. And let me just
Yes.
Can you see my
Yes, sir.
presentation?
Yes, Professor.
Yes, sir.
Okay. Now, before I start the lecture, last time Arvind had asked a question when I was talking about the lightning strike. And at that time, I was not very familiar about how many accidents, serious accidents might have occurred in the history of aviation due to the lightning strike. So I did a bit of a search on Google and I found a few serious accidents which have occurred in the past. But they have been pretty old now. For in recent past, there have been no major failures due to the lightning strike because the aviation industry has become very wise enough and there's enough protection so that serious accidents due to lightning don't occur, although small damages do occur quite often when the lightning strike occurs, but that's minimal and that's already taken into account. That will not jeopardize the safety of the aircraft. So having said that, so I thought, let me just provide you a bit of a, historical failure. I could find the 7 accidents which are reported, but not, I think there were only 2 or 3 which are serious enough due to lightning strike, and others were not very clear. They
Hello?
occurred due to Hello?
Yeah, Mr. Jagan. Lecture has started. Yes.
Okay, so I'll kind of, so one of the accident which occurred quite some time back, what you see on the screen, that is a TWA flight 891, and it occurred in June 1959 in Italy. The aircraft was L1649A Starliner, and normally these lightning strikes would be occurring either in descent or climb, during climb, not in the cruise because that's much higher altitude. And the fatalities were 9 crew and 59 passengers. Now, what happened in this aircraft? Basically, the explosion of fuel vapor contained in the because fuel tanks are really critical, where if there is any spark, then it can catch fire inside. And this is what happened here. Due to the frequent electric discharges during the flight caused by lightning strike, probably it might have not been a very properly designed aircraft at that time, and still the knowledge of various phenomena was still evolving in the aircraft industry. So there might have been some flaw. And that is why the fuel vapors, got ignited and caused this. Once fuel vapor gets ignited, you can imagine the situation, fuel tank picking up the fire, and that's a real hazard. And as I showed last time, say, for the Boeing aircraft 787, I had shown that the remedial action, for 787, for the fuel tanks was similar action is there for others also, but 787 example, which I showed, that they generate the nitrogen. So when the fuel is being consumed and fuel vapors are generated, then the tank is being filled with the nitrogen, which is an inert gas, and there won't be any spark created in the fuel. So having said that, so this is one accident, and then there are other accidents I've reported here, and one can look into Google also. This is a copy from Google. I won't go into the details, and one can always search the details of each accident on Google, basically. But I'll send you this presentation once I finish the lecture so that, it's a final lecture notes you would have. Okay, now let me then go back to if there are no questions on this, I'll start the lecture where we left last time and try to complete this maximum by this week. Hopefully, I should be able to complete. Okay, so I think I left somewhere. So I was discussing last time the repair issues, and I left at that repairs. And then another thing for the testing or compliance is the production anomalies, that when you are producing an article, there would be various manufacturing defects. And normal procedure is when you are designing the article and developing the data for reliables, then you are generating the data reliables for the perfect condition, design condition. Now, everything is not perfect in this practical world. And there might be a situation when in the production, some defects might occur, and they're quite common. Although as you are developing the process, production process is getting matured, the number of discrepancies would reduce significantly. But in the beginning, there might be more. And then you are trying to understand the causes of those discrepancies and what are the remedial actions. So naturally, as the production line gets experience, designers get more experience, then the anomalies also will reduce. But some of the anomalies which I have listed over here, just for the sake of information, in composites, one of the things which happens quite often is the wrinkles. And especially where there's a transition like curvatures, wrinkles might occur there. And of course, in the plane laminates also, they occur. And we had, during 787 program, initially we used to get quite a bit of wrinkles in some of the parts. And a lot of investigations we had done during that time, that how to reduce the wrinkles during the production. So production process continuously was evolving to reduce the wrinkles occurrences, as well as we did a lot of coupons testing. And by the way, what happens when you are trying to manufacture a coupon with certain defects, it becomes very difficult. So we tried to introduce the wrinkles, what was occurring in production, but using the artificial means to produce the wrinkles was not easy. To create the test coupons for similar wrinkles. So we created coupons, of course, whatever we could do with the wrinkle height, wrinkle aspect ratios, and internal wrinkles, outer wrinkles, various types of wrinkles, and tested the coupons for developing the effect of those wrinkles on the strength, like compression, tension, the bearing level, the radius level, and so on. So, I mean, all those people working in the NAL probably might have experienced when they're producing their components that what are the production anomalies issue? Wrinkles. Now, if someone from NAL can eliminate on this, whether wrinkle has been, in production as a defect developed quite often, or they could produce the parts without any wrinkle. Any comments from NAL? If anybody is involved in production of their components? No. Okay. Others is surface depression, then, edge surface breakout, say edge breakout, or drilling. While drilling the fire holes, you get the outer layer. When the drill exit, some fiber breakouts will occur, edge delaminations. So some of these defects are just shown schematically, but the purpose of showing you these defects is because you are engineers working in the industry. When you are trying to develop a product, you need to be mindful of the production anomalies which are likely to occur. And as a designer, one has to develop the alliables or knockdown factors so that you don't reject every component which is produced with certain defect. Of course, you will reject some of the components if that falls outside your limits of acceptance. But you need to develop the limits of acceptance of various anomalies for the production, which are tolerable and which doesn't cause the propagation of the damage and jeopardize the safety of the structures. That's the key. You can't allow every defect to go into end acceptance. You can accept only if it is tolerable and does not cause any safety issues, and you develop a knockdown factor. And the margin has to be always shown to be with that defect. When you are approving it, the margin of safety has to be positive. You cannot accept as a negative margin, by the way. So suppose your design already margin is 0 almost, and you have a defect which knocks down that margin, that means you have to repair. You can't accept it. Okay. So coupon element test, production anomalies I've just listed over here. If you coupon apply, but splices, depressions, porosity, fiber volume fractions, because you will get the laminate which might have higher volume fraction or lower volume fraction than you're designing for. Then you have to develop your alliables for that, or design values, knockdown factor. Alliables are basically for the basic design, and any other values become knockdown factors over that. Fiber volume fraction, resin dryness, countersink depth variations, ply wrinkles, fire breakouts at hole edge during delaminations, cure conditions, cooling and heating rates, cure time and temperature variation, extended cure cycle, off axis. So there are lots of production anomalies for which you have to develop the design values or knockdown factors, the effect of those defects. That's what I would call. Any questions so far? No. Okay.
Hello, Professor.
Yes. Carry on.
Actually, how do we assess, how to know that these defects are actually existing in the component? Do we need to do the NDT, or how to assess those defects so that we can do the test, coupon level test?
Yes, good question.
Yes.
When the part is produced in the production, it will go to the inspection. Okay. And this is a quality inspector who has to check and then consider what is the design drawing saying. And then suppose you get a hole, and hole is being drilled, and you are noticing the fiber breakout on the exit. The layer is broken. Naturally, that's a defect. So the quality inspector has to pick up that and report the defect. That is called Material Review Board, MRB. So that is reporting through NCR, non-conformance report. Say non-conformance report is written by the production engineer. And then the engineer in the design, they evaluate, MRB engineers normally, what is the effect of the defect, whether I can accept it or it has to be repaired. What is the knockdown factor? How much loss in the strength is occurring due to this defect? All those things. So one has to assess. The quality inspector already has been given the design drawings, who has to check every part and report if there is any anomaly. Okay, so did I make it clear?
Yes, Professor. Is that through the NDT? Will the inspector has to do through NDT?
Well, there is an NDT as well as visual inspection. Suppose it's a surface defect, like wrinkles, you will pick up on the surface. And then one can do the NDT or cut up a section. And then what happens? Normally, you would generate some sections and try to assess. It's an elaborate work, in fact, in making the acceptance, especially the wrinkles. Wrinkles is a nasty phenomenon, which could occur where the curvatures are there. Especially suppose you are producing a spar, and the fabric is being laid over the curve. So sometimes what happened during the layup is not properly done. you would generate the wrinkles. Now, whether you can accept the wrinkles, what is the loss in the strength due to wrinkles or the depression? And when they are doing the trimming or during the trimming, the tool is not proper. They can, create delamination at the edges or drilling the holes. Hole drilling, lots of defect come due to the drilling. The delamination at the edges, the fiber break out, and what happens, drill, vibrating, then it will cause the hole a little bit mark away from the main hole. So all those things had to be considered. So all these defects, in fact, I have not listed all the defects over here. Misdrill, that you are trying to drill the hole here, but sometimes drill bit may cut the hole here a little bit. So naturally, you have to inspect it and see whether you can accept those defects or you have to repair. Suppose there is a drill bit which has caused a little bit a notch over here. Now, what do you do to repair? You can't leave the hole like that. So normally, what will be done? You will see whether I can remove, whether, by using a larger hole and using the larger fastener in that, if my fitting and the region can take it, or use a plug, like a metallic plug. So there are different ways to fix those defects, but one has to develop the procedure. I'm sure, these things Anil would be doing because they are producing even if you're experimentally doing the production, naturally, these defects will be there. Possibility is there because everything is not perfect in this world. What I designed the component for, it doesn't mean production is going to be exactly that way. Yes, you aim for that, but if tool is bad, especially drill, if the drill bit is bad or speed is wrong, these cause a lot of defects. The maximum defects in industry come while drilling the holes. Of course, they have been minimized now. I can tell you with a lot of procedures have changed, and in the beginning there were more defects, but later on, I don't think there were many defects coming up in the production. You develop the process, you develop the tools properly with the experience.
Is there any standard, Professor, for this to simulate those defects? Is there any standard?
Well, I won't be able to say the standard, but depending upon that, you are looking, what are your parameters? You want to see, design parameters like bearing strength, the open hole strength, filled hole strength, tension, those, and what is the effect on those strength values due to these defects? And that is what you need to assess. And then you have to see whether these defects are going to propagate. You just can't leave the defect as is. You have to do something about it. You can leave only minor defect if it doesn't do anything, hardly any. But you got to repair them. It's a big area. Let me tell you, it's not that simple to just come out with a solution. The repair solutions, the Boeing evolved over the years, and we used to argue about it. And we did a lot of justification for various repair solutions with the defects. So it's a big area. It's not like 100 hour or 1,000. I know it takes several thousands of hours and immense experience to develop the defects, their acceptance criteria, the repairs. So it's a big area.
That means these defects are assumed to be there in the component itself, or from the actual test, NDT test, we come to know that these defects are there. So we will prepare the coupon based on those defects.
So what happens, depending upon your production process, you would think that you will get some defects. Now you generate the design values with those defects and see what is the effect due to the defect. Now, if it's a very minor defect, you can just do a little bit repair, like filling, and I won't be able to say, various types of repair, but some kind of repair and cosmetic repair, basically. But if it's a big affecting the strength and customer is not going to accept the defects, you have to repair properly, because the purpose is to restore the strength after repair as the strength of a new component. Okay, so it's difficult for me to elaborate. The only thing which I can say, these defects are possible in the production, and of course you have to work to minimize those defects, because it's an expensive process to reject a part and then repair. And sometimes what happens, repairs are not easy to fix. So you may have to scrap the part, and scrapping is quite expensive. So quite often you have to develop a process to minimize the defects. But surely, maybe you can reduce, but sometimes you may get, due to some mistakes in the tool or some process, some defects. And then you have to think of, how do I repair? What is my way to repair so that I can restore the strength? So you have to see the static strength as well as the fatigue criteria. In fact, I was involved in this justification for various defects, and was working to develop the criteria for the acceptance. So it's elaborate. Okay. I mean, I don't know, you're from NL, and whether you have any experience at NL.
I don't know. I'm in structures department, mostly dealing with this mechanics.
I see.
mean,
Okay.
ACD people, they may be doing some manufacturing things. We need to check from them.
Sure.
Yes.
But this is an important area for a production. I'm sure the EDA would definitely be working on these, because they produce or HAL, they produce the components, and naturally during production, the defects definitely are likely to occur, because you just can't develop a process 100%.
And yes. In fact, even I had done one composite fabrication during few years before, maybe 6-7 years before, in connection with my some research work at ACD. I did actually advanced composite division. There I had introduced one delamination, through Teflon coating, something.
Yes,
that I
sure.
But
and that is the way you generate the delamination and then work out the effect of the defect on your strength, stiffness, and then acceptance allowable. And then what do you do? How do you repair it?
But ACD people may be doing routinely this kind of activities.
Sure.
We need to check from them.
Okay.
But in a particular batch, because there will be so many components. Say, for example, some wing, some flap, suppose, say for example, flap.
Mhm.
So in one, so same process will be used for, preparing for manufacturing the, some hundreds of flaps, na, for aircraft, for one aircraft, right, na?
Well,
There
the
will be,
process should
uh,
be similar, but
yes,
depending upon if you are having a component where the drill has to go through metal composite, the drilling is one of the area which require really a lot of expertise when the drills are, components are being drilled, especially during assembly. And it's a very complex area because drilling really introduces a lot of defects also. So that
drilling of
has to be,
composites.
well, composites, yes, separately you can do the composite hole, but what happens quite a few times, assemblies, you have a metallic fitting, you have a composite, and the drill is going through both the components, metal and composite. And that's where the expertise is needed because drill speeds, the way the drills work in metal, it is different in composite. So drilling is a very special area where, of course, the production companies would always have the expertise. They would have developed. I would not be able to answer those questions. I have not worked in production, and I'm not really familiar about various parameters which need to be considered for the production or
So like,
drilling. Mhm.
feed rates in drilling should be controlled.
Oh yeah, well, the feed rate, the speed, and I really can't say how many parameters go into that and what kind of drill, diamond drill, what kind of cutters are there. There's so many. So, it's very difficult for me to pinpoint any particular process.
Professor,
Yeah.
can you please give one example of any of the aircraft components which will have this kind of defects, and those components we are going to test? I mean,
Well,
yeah,
you are not
and
what you
going
do
to
normal. What you normally will do with those defects, you will double the coupons. You are not testing the components. You will make. Suppose I'm trying to assess the effect of the wrinkle. So I'll generate some wrinkles with some parameter, wrinkle height and the weight and the aspect ratios of the wrinkles. I'll produce the coupons and then develop the reliable like a field hole tension, open hole
yes,
compression
yes,
to
yes.
see. Some of those are the parameters which design our components. So naturally, we try to determine those parameters, compression, tension, bearing, and then we say, okay, I can tolerate this much, 2% reduction due to this wrinkle. So in production, suppose this much of wrinkle is occurring. As long as it's not visible on surface, I have to smoothen the surface, and then I can accept this much amount of wrinkle without repair. But if it exceeds my acceptance level, the wrinkle has to be cleaned up and the laid up, relay up and do the repair.
But these wrinkles may vary from component to component. Now, for one component, this kind of wrinkle may be there. For other component, different types of wrinkles may be there.
Yeah,
So for one component,
that is why you develop the allowables for various types of wrinkles and write the parameters.
oh, there means so many variables are there. Delamination may be there for one component at
Yes, you're
in middle, maybe at the end for other
yes,
components.
yes, you are right. And we had done quite extensive work on these
Yeah.
defects, as I was saying. And this is a big program. It takes years of work. Of
Mm.
course, Boeing being a big company, they had to spend money, which cost hundreds of millions on this because they are going to sell the aircraft. Of course, they are selling the aircraft. So they had to develop all that and they have the tools. So it's an extensive program, but for a small company, not easy. It is an expensive process.
Yes, yes.
To do the right things in the aircraft industry. Okay, if there are no more questions, I can proceed further.
Yes, Prof.
Okay, so basically production anomalies compliance, as I've already discussed, production anomalies, you do the analysis, analysis, acceptance, rejection limits, then repair solution. So all the solutions you have to work out, which again I say is not a 1 day or 2 days job. It's hundreds of thousands of hours of job, all this. But it depends upon the program with which you're dealing with. Fabrication process. Now, here I've just typically, schematically, I provided two processes generally fabrication for thermoset resins. One is autoclave curing, another is non-autoclave. And autoclave curing, of course, requires a vacuum. O1 and non-autoclave is cheaper that way. Vacuum assisted resin transfer molding and NAL has produced a part, of course, using a resin transfer molding or VARTM. They call, what is that process? I've forgotten. NAL is calling that process resin transfer molding. I don't remember. And resin transfer molding. So essentially, vacuum assisted resin transfer molding, schematically, the process is you have a tool preparation, apply release agent, then you lay up the preform. Preform has basically, it's a dry preform or dry fabric. Of course, it's not totally dry. It has some binders so that you can lay up and then layers would stick together. So that's a preform. Then you put that in a vacuum bag and suck the vacuum, consolidate the assembly. All of the assembly then is put. So vertically, for a resin transfer molding process, the process is you have a tool and then you have some release film, the preform, which is a part, then some peel ply, and then resin distribution media. Over that, there's a vacuum bag, and then you have some seals. And one side, there was a resin pot, another is the vacuum pump. The reason is it's not a pre-pack with the resin coat. So naturally, you have to wet the fibers in order to get your part. So resin. So you have almost like a dry fabric. So it has to be wetted, and that's why you have a resin pot. And then you're connecting it. So you're sucking the resin through the vacuum. Resin is going through this and wetting your fabric part, and that is all, and then cure it. And then you get a part like NL had produced a box using this type of process, which they call some resin process. I don't know what is the process they're calling it, but surely NL has expertise in that process. Anybody wants to make a comment on that? But I'm sure NL, if they want to consider or understand the process, well, they can go to the production and look at it. They have the expertise in that. And major materials processes. Autoclave, I think I've lost some slide here. I think one of that autoclave slide is deleted from here. I don't know how I'll put that. But autoclave process, of course, what you are trying to do, you are similar process, but you are putting the assembly in an autoclave. Autoclave is an oven which is pressurized and you can heat it up. However, the autoclave process is more expensive because the larger the autoclave, it is very expensive to make large autoclaves for fabricating larger parts. And that is why the resin transfer molding process are being used now, non-autoclave, which are cheaper in fact. But it has its own advantages and disadvantages, which I'm not going to discuss now in this. Autoclave process, VRTM, that is vacuum assisted resin transfer molding process. The materials for that: dry fabric, resin, binder, closed cell foam, sandwich. And for the autoclave is a pre-pack. Pre-pack is fabric or tape coated with the resin. And core for sandwich structure. Now, one of the thing is, if you are producing a component which needs which like a sandwich structures, for sandwich structures, you can't use the resin transfer molding. The only way you can use the resin transfer molding is rather than using a the Nomex core, you need to use the foam like closed cells so that resin does not fill the cells. Because if you have a Nomex core and you are trying to inject the resin, all the cells, the core will be filled with the resin. So naturally, if you want to produce a sandwich structures, normally you have to use the autoclave process. Testing and valuations. So now I consider an important issue over here for certification is testing and validations. We use the building block approach in justifying the design and testing of a component. Now, what is building block approach? Building block approach for testing is a systematic way of obtaining the design information of the composite materials and structures by testing coupons, elements, subcomponent, component. So you are generating, and I'll show you the flow diagram. So basically, you are developing the alliables, then verifying the design by using a building block approach. So basically, it's right to say this is a systematic way of obtaining the design information of the composite materials and structures, which develops the alliables, which verifies the design, and finally gives you the perfect design. Now, here another definition, building a block approach, the substantiation process using both testing and analysis in a program of increasingly complex levels. So you have a testing block, you have analysis block, and this is, inverted pyramid, basically. So testing, increasing complexity for testing and analysis, which provides the efficient product. Now, advantage of the building block approach is reduce program cost and risk while meeting all technical, regulatory, and customer requirements. Because when you are starting from the coupons, build up coupons will generate the alliables, design values, then you are testing some element, then subcomponent, which will verify your design, and then component. So you are following a systematic way of design approach. And what happens if you have a problem, you would know in the beginning rather than in the end. So suppose you're doing I had explained about the point design approach, which does not involve significant amount of testing. Now that becomes expensive because you don't know some of the risks which may be there, and you will know only after components produced, then some unknown risk. So the best approach is the building block approach, by which you will remove all major risks and surprises in the design. So reduce the program cost and risk while meeting all technical, regulatory, and customer requirements, make design development process more effective in assessing technology risks earlier in the program. And this is the objective, that you would know the risk early in the program. Cost efficiency is achieved by, in the building block, by testing large number of small specimens and a fewer full scale articles. Because what you are trying to do, testing small specimens, which is cheaper, you are developing the confidence in the design values and the liables. And then you are using the full scale articles only to verify that. Using analysis in place of tests where possible tend to reduce the cost, reduces the probability of significant surprise in the end of the program. So it's basically a combination of analysis and testing. A schematic building block test. One, if you see this block, which contains the coupons and small elements, which is generic specimens. So what it gives you, database, like liables and design values. Then you test some details, which have that structural design features, just to verify the design features. Because sometimes what may happen, the coupons elements may not have covered the type of the loading which you might get in your details. So you verify the different loading systems which might be there in the elements, details, subcomponent, and component. So basically containing the structural features, and they basically provide and verify the design. Now, the way it works, building a block approach, this I have taken from Mill Handbook 17. It shows three groups, group A, B, C. Now, what does group A mean? It provides you the material specifications and allows development. So first block, material screening and selection. Now, when you are launching a program, new materials, you have to select. Suppose you do not have the materials which are to be used in design. Naturally, you're going to select the materials. So building block one tells you the procedure, what needs to be done in order to select the material and screen it. Second block is, once you have selected the material, then materials and process specifications. The importance of the materials and process specifications is, once you have the material, then naturally you have to develop the specifications so that you can provide those specifications to the manufacturer. And now manufacturer has to supply the material according to your specifications. Now, unless you develop the specifications, you cannot provide the data or specifications to the manufacturer, who has to provide according to your specifications. And that's the important block. Then third one is, after you have got your material, then you are trying to develop allowables and design values, and I'll discuss that. So this is basically group A, material specifications and allowables development. Then once you have developed all the design values using small coupons, then you are doing some structural element test. Basically, they consider the design features, subcomponents. So design values and structural details, design verification. There could be some three-dimensional effect. Some loadings could be different when you test a three-dimensional component, and that will verify your design values. Then finally, you are doing a component test in group C, which is analysis methods and design verification. Now, let's discuss in detail these blocks. Block 1, material screening and selection. So, in material selections, the objective is initial evaluation of new material systems under vast environmental and loading conditions. As I earlier said, you have to select the material, and there has to be some basis of selection of material. Either you just consider, okay, I have the manufacturer like Haxel, they have some material like fabric, resins, or prepack, which I'll just buy from them. Well, that could be fine as long as it's useful to you. But if you're looking for a material which is really optimum for your processes and design, you might have to do the market survey and then select the material based on that. You will assess based on certain evaluations from the manufacturer data and some in-house testing. Select material suitable for production process. Testing involves various physical and mechanical tests. Material screening and final material selection. So you have the fibers, fabric tape, binders, resin, prepack. It's very clear. Fibers are clear. Fabric tape is clear. Binders. Now, what is a binder? Those of you who have got familiarity with the resin transfer molding process, they might be able to understand clearly the binder. Binder, when we are saying the utility of the binder is if you are buying a fabric, which is dry fabric, for your resin transfer molding process. Now, if you lay up the dry fabric, then it's very fluffy. You can't lay up and make a preform. Because suppose you have to lay up 20 layers, what are you going to do? They are not going to stick to each other at all. They will remain separated. So what happens? The fabric will be having some kind of a resin spray, like 3 or 4% of resin will be sprayed on that, or some kind of a nylon film, veil could be sprayed on that so that it becomes tacky. Then you can lay up the layer by layer and they will stick to each other at certain hot condition. You can heat it up and then it will stick to each other so that you can have a compacted laminate. It's not totally compacted, of course, but you can definitely lay up the layers. So that's a binder. Binder could be a resin spray. It could be a film. Many types of binders are there. Then resins, prepack. Evaluation of how are you going to evaluate? You can use the manufacturer data, past experience. If you have a past experience of various materials, use the past experience. You would do the physical test. You would do the mechanical test, some micro cracking evaluation, effect of environment and fluids. And then once you are satisfied with all the properties which you require, then you will be selecting finally the material. So basically several material candidates for evaluation. Properties for evaluation, fiber. Normally you would try to look into the tensile strength, modulus, elongation at break, fiber diameter, density, and the cost. Fabric tape, aerial weight, weave type, drippability, fabric or tape tall, and the cost. Now, you know, I'm not going into the details of each of the property because I'll have discussed various details, the way you have to assess. But these are properties, just a general idea I'm trying to give you now in this lecture. One would try to assess based on that. Screen test resins, uncured, shelf and pot life, gel time at various temperatures, viscosity profiles at temperatures, cure cycle, resin density, ease of processing, that is injectability, density, tensile and compressive strengths and modulus, fracture toughness, moisture sensitivity, adhesion with fibers, glass tension, temperature, dry and wet, material operating limits, thermal coefficient expansions, chemical shrinkage at cure, temperature, coefficient of mixture, moisture. Now it's getting a bit heavy for you people, but each of the property has to be assessed. And naturally, if it's a design program, development program, all these properties have to be evaluated, whether you do your in-house testing or some of the properties based on the manufactured data that is to be assessed. Now, in this, what you see, one of the things which I have listed is material operating limits. What is this material operating limit? So I thought really I might just try to explain the meaning of material operating limits. What happens in the composite, these matrix, which are organic matrix materials, which are sensitive to the moisture and temperature. So with the increase in temperature and moisture content, the properties degrade. So that means your usable temperature depends upon the material properties when they start degrading. So naturally, for this material, when we are selecting the material, we have to see what temperature we can consider as allowable limits for the operation for that material. So the definition is, I've just qualitatively given you here a chart. The mechanical property, that is a wet, with the temperature, and what you're seeing is decreasing, and suddenly, after a certain temperature, the material property degrades faster. And the properties, when they're degrading, they're irreversible. That when you change the temperature back to this one, it doesn't recover. So it's a permanent loss. So naturally, you have to evaluate what is my maximum limit of this temperature, which I can use my aircraft at without jeopardizing the property significantly. So that is why you will try to define a material operating limit. So material operating limit is defined as a characteristic temperature beyond which dramatic reduction in material property would occur. Like suppose open hole compression, which is the matrix control, will degrade significantly after a certain temperature. Same thing with the shear. The reduction in material properties may become irreversible beyond MOL. Okay, now MOL criteria, there are two approaches by which you can define the material operating limits. One is based on the mechanical property, which is normally in-place shear modulus, open hole compressive strength degradation with moisture and temperature. And second is the wet glass condition temperature. So ML is lower of mechanical property and TG approaches. I've shown schematically over here mechanical property. So what you're seeing qualitatively, say sudden decrease in the material property at this temperature. where it could be T degradation we can call, or it could be another, if you're defining with the glass tension temperature, it could be TG wet. So the material operating limit we'll define as some T operating maximum beyond which we will not try to operate our aircraft or material operating. We will design it for that. So there's the margin. So I've defined qualitatively over here, MOL1 is less than TG wet minus delta T1, MOL2 T degradation minus delta 2, T operating maximum is minimum MOL1, 2, and so on. Now I've shown here delta T1 is 50 degrees. So according to FAR, they say your operating limit, it should be the degradation of glass tension temperature minus 28 degrees centigrade or 50 degrees Fahrenheit. Okay. Now, I've said that over here, but delta 2, I don't have any criteria by which I could say, but I think one could say that one could use 50 degrees Fahrenheit for delta T2 also to define this. So, any question on this material operating limit? Okay, screen test, UD tape prepegs, fiber type, resin type, toe size, ply thickness, aerial weight, fiber resin weight fraction, and the shelf life. Tape prepeg continued, cure cycle, tensile strength and modulus, compressive strength and modulus, fracture toughness, moisture sensitivity, glass tension temperature, dry and wet, material operating limits. Fabric prepegs, I will just pass this quickly because they are similar as we have said for the tape prepeg, so I'll not repeat it. Binder material, what are the tests normally you could do? Binder provides the bonding to dry fabric for preforming and may enhance interlaminar fracture toughness. Evaluations include fabric adhesion characteristics, glass tension temperature, processability, density, aerial weight of binder film, effect on fiber matrix interface due to binder, and effect of binder microcracking. So various properties one would try to evaluate. Again, I won't go into the details. Now, screen test. Basically, one could use these coupons like what I've shown. Schematically, 0 degree unlost tension, 90 degree unlost tension, 0 degree unlost compression, 90 degree unlost compression in plane shear, open hole compression, open hole tension, CAI, and then the fracture toughness test, double cantilever beam G1C and the edge notch flexure G2C test. So various tests. Again, I'm not putting the details because I've just shown schematically various coupons one could use. Cured laminate physical properties, assessment, fiber volume fraction, voids, porosity, density, glass tension, temperature, laminate thickness variations, moisture absorption behavior, laminate hydrothermal cycling, and matrix, also microcracking investigation. So various tests. Effect of fluids for evaluations, various aviation fuels, lubricating oil, hydraulic fluid, de-icing the fluid, MEK. So various aviation fuels, one has to consider the effect on the composites. So there is standard test, which are provided in ASTM standards, and also MIL Handbook 17 provides some details. One could look into that, but it is necessary when we are trying to evaluate the new materials, then we have to study the effect of various fluids. And generally, the test for fluids would be the critical properties for the matrix, which are normally open and compression, and the shear modulus and strength, and some physical tests like a fluid absorption, weight gain, and microscopic examination of any microcracking. Laminate microcracking evaluation. Generally, what happens when you're trying to evaluate the microcracking, because microcracking we cannot accept in our composite materials. Some materials might have a microcracking due to environmental effect, and we have to discard that material. That's why we had to do some testing to understand if there is no microcracking occurring. Generally, what happens is a schematic test. Example I've given you here. What will happen? You will make the coupons, you will soak them at certain temperature and some humidity level exposed to the equilibrium, and then you run the thermocycle on that. And during that process, when you are doing thermocycling, you will be taking the coupons after certain, like 200 hours or 500 hours or 1,000 hours at various intervals, and try to examine the microcracking by sectioning them and then using a microscope examination of the coupons for any microcracking. And then you will assess it. Okay, there are 1 or 2 cracking after 2,000 hours or 1,500 hours, you might accept. But if there's significant amount of microcracking, you will reject the material and then see another material which doesn't develop the microcrack. And this is an important issue for the composites. Block 2, materials and process specification. Any questions so far on this? It seems to be pretty dry, isn't it? Materials and process specification objectives. Specification development to control the purchase of critical material. Effect of process variables on material behavior. Qualification of the material to assess that the material does not change substantially with time, to establish acceptance, equivalence, and quality control values. So basically, these 2 items are very critical. This one and this one. That is, to purchase the material, you develop the specifications, and then to establish acceptance, equivalence, and quality control values. And how you do that? You will be testing different coupons for different properties and generate the values for material specifications. And so material specifications are developed by testing coupons for mechanical and physical characteristics for several batches of materials and environments. Like this is the same picture which I showed you earlier, so similar coupons are done. Physical test, light thickness and all that, I'll skip that. Material specifications, data analysis. And I've given you the reference, so suppose somebody wants to, I'm sure the NL probably might be using some reference if they've developed the material specifications, but if not, some students, so they want to understand how do you analyze the material specification values, then this is one of the references I've given this one, which could be used, or Mellon Book 17 could be used. What you do here, when you have done the testing, then you will try to determine the maximum individual values and minimum individual values. There are some statistical method given that reference. And so V minimum individual is mu minus K1 sigma, and maximum individual mu plus K1 sigma. That is, mu is the average value and sigma is standard variation. And K1 are the parameters which are given by that reference. And minimum maximum average values are given by this, where K1, so mu is mean, standard deviation, K1 extremum parameter, K2 mean parameter, and all this details are in this. I'll not repeat that. And then you will develop a report or a material supplier, where various properties like minimum individual, minimum average, maximum individual, maximum averages, you'll provide based on this analysis, give it to the supplier and your quality control department, material supplier, then will supply you the materials who have to comply with your requirements because they would be doing the conformance testing when they are supplying the material, and then you'll be comparing the values. And sometimes you might also run in-house just to check or verify those values. Allowance and design values. Now, any questions so far, please do ask. Or is it not useful? Hello?
Yes, sir, it is useful. We'll ask, sir, you please complete. We'll find some questions.
Okay.
I think.
So allowables and design values now. Material allowables, as per 613, material strength values must be based on enough tests of material meeting approved specifications to establish design values on a statistical basis. So basically, the allowables are developed using a statistical basis. So material design values must be chosen to minimize the probability of structural failures due to material variability, except as provided in paragraph of this compliance. So purpose is provide firm material allowables suitable for design, effects of layup, stacking sequence, laminate thickness, environment, notches, joints, radius, sensitive to fabrication process, cure conditions, fabrication anomalies, repairs. And what is the definition of allowables? Just to highlight, some people, to give you the idea, what do they mean by A basis or B basis? So here I provide the definition. So allowables, the definition is lamina and laminate test data on a probability basis. So you could define in terms of the A basis or B basis. What are the A basis and B basis? The definitions are written over here. A basis is when 99% of values in the population lie above the A basis value with 95% confidence. So what happens when you are designing with A basis? That means only 1% of the data. There is a probability of only 1% that the value might be lower than your design value. So normally this is applicable to single load path structure. When you don't have the redundancy, you have a single load path, that's where A basis is used. Otherwise B basis. So what is B basis? Rather than having a 99%, here 90% of the values in the population lie above the B basis value with 95% confidence. That means 10% of the data could be lower than your B basis. But that is acceptable because you are designing the structure with a multiple load path structure. So there's some redundancy in it. And that is why B basis. What is design value then? Yeah, we have defined A basis, B basis, but design value, basically a material property or load value that takes into consideration some program requirement. That is in addition to those allowables developed using a statistical basis, you might apply some kind of a fitting factor, some scaling factor, some cutoff levels. And that is how the design values could be provided. determined from test data and chose to minimize the probability of structural failures due to material variability of some. So there could be some criteria you could define. So in a schematic chart, this is all data. And so basically this is a line, A basis line, and this is a B basis line. So you can see here, some data, they're all live. In fact, I should have put some data below this line and one data over below this line, but nevertheless, A basis, B basis. Criteria for test matrix development. When you're developing the test matrix, then you try to develop based on the ply modulus, tension, compression, shear, ply positions ratio, strain to failure, and laminate modulus for tension, compression, and shear, laminate positions ratio, strain to failure, nose strength, basically filled hole, open hole, tension, compression, bending. So various values you need to generate when you're trying to develop the allowables, because all these parameters you would need in order to design the structure. Design specifications, because you'll have some joints, holes, notches, radius, etc., compression after impact. So whatever the features you want to cover in your design, you need to develop the design values and allowables for all those features in your design. So you'll develop the coupons, test them, develop values. That's the purpose. Parameters variations, there could be parameter variations like layup, envelopes, geometric parameters, damage types and sizes, environments, loading conditions, fabrication process, certification requirements. So when you are trying to develop your design values, suppose you are developing the open hole compression. Open hole compression in your design structure, there would be different layups, different thicknesses, environments. You have to cover the cold environment, you have to cover the room temperature, you have to cover hot, wet conditions. And so that way the test matrix multiplies rapidly. So typically, say I've shown here, ply level test, 0-degree tension, 90-degree tension, 0-degree compression, 90-degree compression, in-plane shear. And the properties we are trying to determine: modulus, Poisson's ratio, failure strain, failure stress. And you are testing for multiple batches and replicates, various environmental conditions covering. So there will be hundreds of people, although they are looking only say 3 to 5 test type, and in each one, suppose you are having a 1 parameter variation, 6 coupons for one, and there could be several parameters. So that means this test matrix would have almost hundreds of coupons only for this one. And this is not the only test, then you're having a laminate level test, and so on. Now, laminate ply and laminate mechanical arrivals and design outputs. So basically what you are trying to do from ply modulus and failure strain outputs, you are determining the ply modulus, Poisson's ratio, and compression, tension, shear. And normally what happens, we don't do the statistical analysis for the modulus. So remember that. It's important, the design, that normally the modulus is calculated on the average. You do the statistical analysis, A basis or B basis, only for the strength values. So it could be an important criteria, all those who may be thinking of designing and developing the allowables, that modulus as an average value, no statistical analysis performed, but strength B basis. when you are trying to determine the modulus could be defined as a chord modulus or a secant modulus. So I've shown you generally a schematic diagram here. Stress and strain. So ply modulus is generally defined as secant modulus or chord modulus. Secant modulus is like ES4. I have shown like a ES4 equal to S4 upon E4. Suppose S4 upon E4. And chord modulus between two strain values. So this is chord values, chord modulus, S4 minus S1. So strain value is chosen for the modulus calculus depending upon organization, whether they define as a chord modulus or a secant modulus. Modulus should be calculated in linear region with stress strain curves. That's the criteria. Okay, limited mechanical test. I will test. Test type, unknown tension, unknown compression, modulus property. You determine the modulus, field strain, stress, and various like tension, compression. I would skip this. Test parameters, various thicknesses, layups, diameters, coupon width to diameter ratio, hole pitch spacing, countersink hole depth, fastener types, and diameters. So various test parameters you have to cover. And as I earlier said, when you are trying to cover all these parameters, your test matrix could develop into a couple of thousand coupons.
So, sir, Professor, these are the test parameters for the allowables.
Yes. So
How
when
about
you are,
yeah.
the reason being, because your design would have different hole sizes, the fastener sizes, the layups, variations. So you need to cover all those conditions. So when you are trying to develop the allowables, you need to develop the allowables considering all those variations which go into the design.
Yes, yes.
Yeah.
But how about the design value?
Well, then what you are trying to do, the design value, you are doing the statistical analysis of the basic parameters. And then the variations from that you would cover as a knockdown factor. So basic values will be done, the allowables, based on the statistical basis. And then your various parameters, what you will be doing, you will test a few coupons for that variations. And using the factor like average to average, you will determine a knockdown factor. So this is a process.
When something has not been considered in deriving the allowables, those parameters you have to consider in getting the design values. That is what?
No, allowables. Basically, it's a part of allowables. I'm not differentiating allowable and design values.
Okay.
You know, everything is allowable for me.
Can you please explain through one example, Professor? This.
Yes. Suppose you are determining the open hole compressive strength. So open hole compressive strength, you are considering for a layup, which is quasi-isotropic.
Yes.
Okay, 16 ply. Suppose you are using tape, so 16 ply quasi-isotropic. Where 25% 0, 25% 45, so 25% 90, and 50% 45. Okay. Now, you design what happens, making the coupons like quarter-inch hole and testing for various batches. That is another thing. You have to determine the values for different batches, like 5 batches or 6 batches of materials. So that means almost like 25, 30 coupons you'll be producing. You have done the statistical analysis for that parameter, which is just a quasi-isotropic and thickness of like 2 millimeter thick coupon. Okay. Now, what happens? This you have done at room temperature. But you want to determine the property at hot wet condition also. So you will do, I'll make the quasi-isotropic coupons for hot wet conditions, test it hot wet condition, determine the value. And once you determine the value for that, then using the value of that hot wet condition, room temperature, compare that, what is the ratio, knockdown. So using that knockdown value, that's a 20% reduction, suppose. So you will apply that 20% knockdown value for hot wet condition over your design value. Suppose earlier my open hole compression value for a baseline coupon was, say, 6,000 microstrain in terms of strain. And knockdown factor with the environment is 20%. That is 80% value. So that means at that environment, I'll get around 4,800 allowable. That's what I'll use. So you will generate the charts for various parameters effect. And I've shown some schematical example over here, like actually, sorry, it has gone in the hands. Oh, come on. Just sorry for that. I clicked the wrong button. Okay, let me just try to explain here. I'll just skip this. Data analysis. So when you have developed for material batches, as I was telling, say like quasi-isotropic laminate with different batches of materials and say 30 coupons, then you will do the statistical analysis, determine A basis or B basis. The procedure you can use is based on the Mill Handbook 17, and there's a program available in public domain from National, that is a National Institute of Standards and Technology. In fact, one can download this recipe program and use that program in order to determine the allowables. You don't have to write the program, software, this available software which one can use to determine the allowables. So suppose you use that. So using that procedure, you have determined the V design value. Sorry, allowable design value has been determined using this program, and that gives you V design baseline. Basically, say quasi-isotropic laminate, when I was talking, suppose, using the statistical analysis, you had determined the base design value, baseline. And when you have developed the parameter like humidity, moisture parameter, the hole size parameter, all those variations you can apply as the average value. So determining, you test the hot wet coupon, you test the room temperature, which you already have, compare the average values, determine the knockdown factors, and then develop some kind of a parametric curves, like suppose this is a strain, percentage 0° fiber, environmental behavior, hole diameter, thickness. So you will develop charts like that. I could go into the depth of this one if time permits, and if somebody is interested in detail later on. But in summary, what you are trying to do, you are developing the allowable using a statistical analysis for some basic parameters, and then subsequently, all those other parameters like percentage of the different fibers, then moisture and temperatures, hole size, or different parameters, you will generate based on the average to average ratio and generate the charts. That is how you will generate the heaps of allowables design values, covering all of your design envelope. The purpose here is to cover your design envelope and the environments for which you are designing the structure. Is it clear or require more explanation? Maybe next time I might
These are the
explain.
coefficients.
Yeah,
These are the some factors to be multiplied. What do we understand with the allowables?
yes,
Yeah.
that's right. Depending upon suppose temperature, your temperature is here for design, then you will generate say C and V multiply with this parameter. And that is what I've shown here. Say V design, that's a design value you are trying to determine, is based on C1, C2, Ci. See, these C's are basically those parametric effect on your design value. Maybe what I'll do, I'll prepare another slide. I'll show you a bit more in detail to explain how you do it.
Can you please, Professor, solve one problem actually, so that to understand these methods, if you can, if it is possible, Professor.
I'll try to do that, but may not be. I'll just show some tabular thing. Okay, let me see what best I can do. Just hypothetically, I might just put some value.
Yes, yes, yes. That's what, to understand the method. Yes.
Yeah. Okay. Done. Anyway, nice. 9 o'clock here, and I might close this lecture. If there are more questions before I close.
So when we were talking about the properties, why do we not take a statistical basis for modulus? Is it because of the modulus not being very affected in general, or is it because modulus is not seen as a direct, failure criteria?
Good question. Generally, what happens with the modulus does not vary significantly. So you are testing various coupons, and then you can determine the average value. Even if you try to do the statistical value, you may find because the variation is so small, you may not get much of a benefit out of it. So generally, the modulus is normally considered to be an average value rather than strength. Strength varies quite a lot, but modulus does not. Modulus, of course, it gets affected. Suppose the volume fraction, but we do consider the effect of the volume fraction because stiffness modulus can be affected by various parameters, and you do account for that. But for a baseline, when you are doing a quasi-isotropic laminate, and what you will find from one coupon to another coupon, the strength would vary. It can vary by 10%, 15%, but modulus will never vary by 10%, 15%. Maybe or 2%, 3%, not substantially. And that is why generally the modulus is considered to be an average value, because there's no significant variation.
Okay, so I understand. Yeah,
But,
thank you.
but as I said, when your parameter variation is there, like fiber, different percentage of fiber, or layup changes, naturally variation of there. So you have to determine, of course, with those parameters, the variation of modulus. But for one parameter, there may not be any variation. So that's a general philosophy, modulus. But surely, if one wants to do the statistical analysis for modulus also, one can do it.
All right, so thank you.
There is no rigid rule that you have to do only the average. But as I said, there is no significant variation, and that is why modulus could be considered as an average value. Okay, but it's a good question. I was asked earlier also by somebody.
Oh, yes, sir. Thank you.
Any other question? In fact, this is, these blocks, when I'm showing the building block approach, it's quite interesting details. And when you are working to evolve a new design and working in an industry, all these blocks become very important because that's the key to generate your design and verify. So building block approach is the approach which is crucial for aviation industry. It is described very simply in that, but when you develop a program, it costs billions of dollars for a new program to fulfill the requirement of this building block approach. That's what it is. And as I said, just for one material, developing all these allowables would cost you tens of millions of dollars. So it's fairly elaborate program for industry, for a new, like 787 program, which was new program for these new materials. And I've gone through that. I've seen how rigorous testing has to be done. Okay, any other question? I hope that on Friday I can wind up the remaining portion. I hope this will be useful to all of you, this building block approach, which I've been discussing, although I've been running a bit fast, but I thought some of the slides quite repetitive, so I didn't have to go into the details. But if somebody has any questions on this, I'm fairly open for that, for going into the detailed discussion, because I'm very familiar about the building block approach, which I've gone through during 787 program. So I'm fairly confident about it, what needs to be done, what testing, various, procedures. So basically elaborate program I've been. So I've been lucky to be involved in that program, which was quite extensive. Okay, if there are more questions, then we can close today. However, if anybody has any questions on this, you can always send the email to Professor Dinesh, or you can send it to me. I would be happy to answer the question.
Sure, Professor. Thank you.
Okay. All right.
Thank you, sir.
Thank you very much.
Have a good evening.
Friday.
Bye. Yeah, Friday we'll